Or two. Okay. Let's hope that works. And make sure my screen is still being shared. What meeting? Let's hope it's actually recording. It's right now it's in a superposition of recording and not recording until we take a measurement. Actually fits perfectly for this lecture. All right. So it's 8 o'clock. We should probably get started. My name's Ben. I'm a master's student in the computer science department, and I'll be filling in for Tino this week because he's off giving a talk to people in Texas. So yeah, he has to talk about the jokers that he's doing research with. I am one of those jokers. So the plan for this week is to start talking a little bit about quantum stuff. So first thing I'll try to get through today might be a bit ambitious. We might not get all the way through, but I want to talk about like gates, states, and then eventually try to get to entanglement and quantum teleportation. And then next lecture, talk about the BB84 protocol, which is a bit more into quantum cryptography, which I wouldn't make a ton of sense to talk about quantum stuff without talking about quantum cryptography in the cryptography class. So we'll definitely get to that at some point. At the end of last week, Tino started talking a little bit about quantum states, right? I think he mentioned the general form of a quantum state, and then mentioned that quantum gates are unitary. Does that ring a bell? Or did he not mention that? He didn't? Okay. Anyway, I'll get to that today. So for classical computation, remember that our bits were just elements of the set 0, 1. You either have 0 or you have 1 is your bit. Oh, shoot. Another thing I should mention is I might breeze through some things pretty fast. If you have any questions, feel free to stop and ask me. Or I've also got Luke over here who will hopefully we'll be able to figure out if I'm going too fast or breezing over some things. So my background is in physics, so we don't do the proofs as much. So be warned about that a bit. Yeah, classical bits are just 0, 1. We have the bit strings, zeros, ones. We have 2 possible values. With quantum bits, or we call them qubits, these guys, and the notation that we use to denote a quantum state, it's Dirac's bracket notation. So if you see this here, this is a ket, because it's like the left half of a bracket. This would be the bra, because it's, no, this is the right half of the bracket. This is the left half of the bracket. You throw them together, you get a bracket. Yeah, physicists are great at naming things. But our states, or our qubits, are elements of this complex 2 space, and they take the general form size equal to alpha ket 0 plus beta ket 1, where these guys, ket 0 and ket 1, are the rectilinear basis states. Which the rectilinear basis is just a fancy name for the Z basis, or the basis where we have, let's see if I can get some different colors here. Okay, now my pen is thicker. What did I do? Okay, there we go. That should be better. Okay. ket 0 lies right here, and ket 1 lies right here. And our arbitrary quantum state is just some linear combination of these two basis states, where alpha and beta are potentially complex numbers. Yes, that's a good point. And ket 0 is just the 1/2 vector 1, 0, and then ket 1 is 0, 1. Yeah, one of the nice things about quantum computing is the word quantum sounds very scary, but really it's just a linear theory. So for the most part, we'll be dealing with 2x2 matrices. We might have to go up to 4x4, but even then there's a fancy little trick that you can do to turn it into 2x2 matrices. Yeah, Luke loves that trick. He could tell you all about it. All right. So then another thing that needs to be, or condition that needs to be put onto our quantum states is this right here. The norm squared of alpha plus the norm squared of beta has to be equal to 1. And this is called normalization. All quantum states have to be normalized. And the reason is because what this guy here represents, or is, it encodes a probability distribution. So this, if we take a measurement, say, of our state, and a measurement gate usually is represented by this symbol. If you don't see any other letter denoting what basis it is, generally it's going to be in the rectilinear basis. If you see something like a D here or somewhere else, that means it's a measurement in the diagonal basis. And the diagonal basis is just a different basis. I'll get to that in a minute. But if we measure our quantum state, what we end up with is ket 0 with probability norm squared of alpha, and ket 1 with probability norm squared of beta. So any probability distribution, the total probability has to add up to 1. And because of that, we have to impose this normalization condition on our quantum states. Then another way of writing the same condition using bracket notation is this here. This is equal to 1, where this here is just this ket, and then this part here, the bra of psi, is just the conjugate transpose of psi. And then this, or the conjugate transpose, is we take our vector, we take the complex conjugate, and then we transpose it. So if you ever see me draw that little dagger or what looks like a plus, that just means take, say we have matrix A, B, C, D. We want to dagger it. We just take complex conjugate of all the elements and then transpose the matrix, which gives us star. Gives us this. Or this, also the kind of linear algebra way of looking at it, is it's the inner product of this vector with itself in complex space. So this guy, if we have size equal to alpha ket 0 plus beta ket 1, in vector notation, this is just alpha beta. So if we take the conjugate transpose of that, that's going to give us alpha star beta star, where the star here just represents complex conjugation. I think sometimes you'll also see it as just alpha with a bar over it. I think this notation might be used a bit more in mathematics. at least from what Luke tells me. But then if we take this inner product here, we get alpha star, beta star, beta, and this is star alpha plus beta star, beta, and this has to be equal to 1, but then this is just the same condition, but written in the more physicsy kind of way. Does that make sense? Is everyone following, or have I lost everyone already? Okay. And then there's a little bit on measurement. So now I think a natural question that might come up is, okay, we have this rectilinear basis, and the rectilinear basis is nice, but is that the only basis that we can represent quantum states in? Like, does everything have to be rectilinear? Or can we have other bases? And the answer to this question is yes, we can have other bases. As long as we have, say we have a set of basis kets. Actually, let me just do the 2x2 case. I think that'll be easier to see. So say B1 into B2 are just two kets. The conditions that we look for when creating a basis are the inner product of a basis ket with itself has to equal 1, and then the inner product of a basis ket with another basis ket has to equal 0. This here is orthogonality. So if you've seen that in a linear algebra, it just means that our two vectors are perpendicular to each other. And then this is normality. And then the reason we need this is because of the normalization condition needs to be satisfied. So another popular basis that's used is the diagonal basis. Let me add a pen, make this one green. There we go. Where we have ket plus, where ket plus equals 1 over root 2 ket 0 plus ket 1. And this is just in terms of the rectilinear basis states. And then ket minus is equal to 1 over root 2 ket 0 minus ket 1. And these guys look kind of like that.
Notice that when you square 1 over 2, you get 1/2. That's the probability of the measure.
Yep, exactly. So it's an equal 50-50 probability of getting either ket 0 or ket 1. And then another thing we could do is we could write our general state psi here as a linear combination of these two guys instead. So let's say just alpha tilde ket plus beta tilde ket minus. And then that's also a valid way of writing this. Okay. Does that make sense for the most part? Okay. So now we have these quantum bits, and these allow us to store our information. Now, what can we do with them? Right? Like we want to be able to do cool things with our bits. We want to be able to transform information, do that type of thing. So that's where gates come in. And a quantum gate, let's call you a quantum gate. It's just a matrix. For a single qubit gates, it's going to be just a 2x2 matrix in complex space. For multi-qubit systems, you might have higher dimensionality. Sometimes you can reduce them down to 2x2. Block matrices. Block matrices are a very fun tool to use. But now something we might be asking is, okay, what conditions do we want to impose on these gates? the way that we apply a gate is we take our state, we feed it into the gate, and then out comes a new state, call it psi tilde. Can anyone tell me something that needs to be true about this new state here for it to be a valid quantum state? Or what has to be true about its inner product with itself? In order for it to be a valid quantum state. Exactly. Because if this didn't equal 1, then our probability, or the sum of all probabilities, of getting all the states wouldn't equal 1. And then it's like, oh, shoot, I threw this into my quantum gate. Now I've got a 70% chance of measuring ket 0 and a 90% chance of measuring ket 1. Uh-oh. That poses a bit of a problem. So we need gates that preserve the norm of the vector. And then these gates this is what requires them to be unitary matrices. And what a unitary matrix is it's a matrix that follows this condition, where it multiplied by its conjugate transpose is equal to the identity. And the reason where this comes from is, say we take a look at this inner product here. We break it down. We have psi tilde, but then we know that this psi tilde is just u times psi there. But then this cross psi tilde we said was just the conjugate transpose of the ket. But then the ket we know is u times psi dagger. And then when we apply the conjugate transpose, we flip the terms, transpose each. So this gives us this, and then this is just this here. So if I take this, throw it into this equation, we get and then this is true if this guy here is the identity matrix. Because remember, we had this condition has to hold true. So if this is the identity, this holds true, we preserve the norm, and we're good. So our quantum gates are unitary gates. And then this reasoning isn't necessarily terribly important to know that this was just my attempt at trying to prove something. I don't know, Luke, how did I do? It was fine. Okay. So some fairly common 2x2 quantum gates. There's 3 kind of here that go together, the Pauli gates. So sometimes you'll see the Pauli X gate denoted as sigma X. Sometimes you'll see it as big X. I think in actual quantum computing, you see it as big X more. In physics, you see it as sigma X more. And this is 0, 1, 1, 0. And what this guy does on a rectilinear basis state is it flips a ket 0 to a ket 1, or it flips a ket 1 to a ket 0. And to see this, let's see if we apply X to ket 0. That's 0, 1, 1, 0. Ket 0, recall, is 1, 0. So this gives us 0, 1, which is ket 1. And then it does the same thing for ket 1. It flips it to ket 0. Second Pauli gate is the Z gate, denoted as either big Z or sigma Z. And this is 1, 0, 0. minus 1. And what this guy does is if you apply it to ket 0, 0, 0, minus 1, 0, it is going to just preserve that. So z on ket 0 is ket 0. Then if you apply it to ket 1, it's going to negate it. Because this 1 here multiplies with this negative 1 here, and you get 0, negative 1, which is negative ket 1. And then just for completion's sake, the Y gate is this guy. We won't really run into this guy much, so don't worry too much about it, but he is there. And these are known as the poly gates. And then the other 2-qubit gate that we'll run into a lot is the Hadamard gate. It's 1 over square root of 2, 1, 1, 1, minus 1. And then what this guy does on ket 0, we have 1 over root 2, 1, minus 1, 1, 0. This is going to essentially pick out this first column. We get 1 over root 2, 1, 1, which is equal to 1 over root 2 ket 0 plus ket 1, which is equal to ket plus. And then we apply the Hadamard onto ket 1, we get ket minus. So the Hadamard gate allows us to go and take a rectilinear basis state and turn it into a diagonal basis state, which is nice. Or the other thing it allows us to do is it lets us get an equal or uniform superposition of the rectilinear basis states from a single rectilinear state. So we'll see that a little bit. This guy's going to pop up again. Okay, so now we've got states and we've got gates. But we've only so far looked at single qubit systems. And single qubit systems are fun, they're interesting, but we really want to be able to deal with more than one qubit, right? Like one single bit systems in a classical computer are nice, but we want to be able to do a lot more with a lot more bits. So how do we deal now with multi-qubit systems? Or how can we combine our vectors together in such a way that allows us to extend them up? And the answer to that is the tensor product, which again is another one of these things that it sounds a lot scarier than it really is. And to be fair, anything with the word tensor in it sounds kind of scary. But say you have two matrices, let it be A, B, C, D, and then another matrix B, the tensor product of A with B, and we denote the tensor product as this multiplication symbol with a circle around it. What we do here is we take we take our second matrix and just multiply it onto every element in the first matrix. So this then is going to be A times big B, B times big B, C times big B, and D times big B. So it's simple enough in terms of what you actually have to do. It just sounds scary. And anytime you have an operation, you throw a circle around it, it makes it look a lot scarier. Like, I can't wait until I see an equal sign with a circle around it. It's like, oh goodness, what is that symbol going to mean? But okay, so now that we have the tensor product, just to get a bit more familiar with it and see, let's take a look at our 2-qubit basis states. So the first one is going to be ket0, tensor ket0. And there's the other way that we commonly denote this is just ket00. This notation, like if you see ket A, B, this generally means ket A tensor ket B. It's just a convenient shorthand. Yeah, I won't show the other one. So this guy, ket0, is 1, 0, tensor 0. Remember, we just take this guy, multiply it in here, and then multiply it in there. So 1, 0, 0, 0. This is 1, 0, 0, 0. And notice now that we have a 1/4 vector instead of a 1/2 vector. And then for the 3 basis states, it'll be 1/8. So one thing the tensor product kind of does is it makes our dimensionality explode. But we won't have to worry too much about that here. So then second one, ket0, tensor ket1, denoted as ket0, 1. 1, 0, tensor 0, 1. Same kind of thing here. We get 0, 1, 0, 0. Ket1, tensor ket0, 0, that's 0, 1, tensor 0, 0, 0, 1, 0. Does anyone want to take a wild guess as to what ket11 looks like? We've got a nice little pattern for me. This is 0, 1, 0, 1, 0, 1, 0, 0, 0, 1. So now note that I'm going to add another pen, a blue one this time. We just, this here is 0 index, this here's the 1 index, this here's the 2 index, this here's the 3 index in the vector, and then for higher would go further. But let's decompose these into the bit patterns actually. So the bit pattern for 0 is 0, 0. The bit pattern for 1 is 0, 1. The bit pattern for 2 is 1, 0. And the bit pattern for 3 is 1, 1. So notice that ket0, 0 has a 1 element in the 0, 0 component of the vector. The 0, 1 has a 1 element in the 0, 1. 1, 0 has one in the 1, 0. And 1, 1 has one in the 1, 1. That's actually really convenient. And this, if we go up to 3 qubit, 4 qubit, 5 qubit states, this generalizes. So the basis state for some general ket B, if B is a bit string, is zeros everywhere except for in the index numbered with whatever the decimal number for B is, where you have a 1. We all feeling like experts with the tensor product now? Don't worry, I've been doing this stuff for a few years and I'm still not an expert with the tensor product. So then, yeah, a couple other properties that the tensor product has is it's both distributive and associative. So if you have like A tensor product B tensor product C, you could do that in any order, and A tensor product B plus C is just A tensor B plus A tensor C. So we can distribute it over addition. Those are really nice properties. Okay. Now let's take a look at a multi-qubit gate. because now we've got multi-qubit states, we might as well start looking at, okay, what happens if we want to do operations on multiple qubits? So there actually, one thing that you could do is if you have, say, a 2-qubit gate, let you, the 2-qubit gates, you could, or be 1-qubit gates, I mean. So if these are 1-qubit gates, you could construct a 2-qubit gate by constructing the new gate U tensor product V. This is going to be if they're 1-qubit gates, so this is 2 by 2, this is 2 by 2, this is going to be a 4 by 4 matrix. Then another neat thing that the tensor product does is, say I feed U tensor V into ket A. Let me go like ket psi 1 tensor psi 2. These terms here are going to go together, and these terms here are going to go together. So this is actually going to give us the state U psi 1 tensored with V on psi 2. That is an awful V. Okay, there we go. That's better. So these two guys go together. These two guys go together. That's another nice property of the tensor product. That's one way that you could make a multi-qubit gate. Another, there are also, though, some just multi-qubit gates that we don't really get from doing this type of thing. One example is the controlled NOT gate, which classically, what the controlled NOT gate does is it takes 2 bits, A and B. We feed them into the C0 monster. Out the other side, we get A, and we get A exclusive or B on the bottom here. So if we input 0, 0, we get 0, 0 at the other end. We input 0, 1, we get 0, 1. We input 1, 0, we get 1, 1. If we input 1, 1, we get 1, 0. So if A is 0, we keep the second bit B. If A is 1, then we flip the second bit B. And if I put this in matrix form, let me just index by bit string here, 0, 0, 0, 1, 0, 1, 1. The 0, 0 to 0, 0, we have a 1 there. 0, 1 to 0, 1, we have a 1 there. 1, 0 goes to 1, 1, so we have a 1 here. And then 1, 1 goes to 1, 0, we have a 1 here in this element. And then, obviously, zeros everywhere else. Big 0, just that this is just 2 by 2 matrix of zeros. So nice thing about this matrix here, C, is that it's a unitary matrix. Okay, so if it's unitary, then we might think, okay, let's try using it as a quantum gate. So this is the quantum C0 gate. And then in the quantum type of notation, it looks like you feed in ket A, ket B into the C0 gate. I just like calling it capital C, just because C is nicer for the matrix notation. I think Tino uses just C0 when he draws it, maybe. Yeah. Then out the other end, we get ket A, and then ket A exclusive or B. Then another thing to note about this matrix is here we have 1, 0, 0, 1. This looks an awful lot like just the 2x2 identity matrix. This is a matrix of zeros. This is a matrix of zeros. And then this guy here, 0, 1, 1, 0. Well, if we go up here, this is just the X gate. So I could just put an X there. So here now we've got just a 2x2 matrix of 2x2 matrices, which that's a fun trick that you can sometimes play to reduce from a 4x4 problem to a 2x2 problem. I really like doing that. Luke has his opinions. But yeah, this is the quantum C0 gate. And then, yeah, let's see. See what happens on each of the basis states. So we have C on ket 0, 0. What this is going to do is it's going to pick out this column, because remember the ket 0, 0 is 1, 0, 0, 0, gives us 1, 0, 0, 0. So this is ket 0, 0. C on ket 0, 1. It's the same thing. C on ket 1, 0 picks out this third column, which is 0, 0, 0, 1, which is ket 1, 1. And then C on ket 1, 1 is out fourth column, which gives us ket 1, 0. Or you take this and exclusive OR it with this, and that's what gives you the second bit. Okay, is everyone following me still, pretty much? Lost in quantum space? That's which is a valid place to be. Quantum space is kind of confusing sometimes. Exactly. Yeah, and we'll get to breaking the universe pretty soon. Breaking the universe is fun. Okay, but now we've got some states, we've got some gates, and then we've extended that up into multi-qubit states, multi-qubit gates. Now, I think the next question is how do we do cool stuff with it? Like, how do we take these bits and gates and apply them and make them do things? So when you're looking at, say, a classical computer, you have bits and then you have your gates. You've got your C0, you've got your OR gate, your AND gate, your NAND gate, whatever gates you want to play with. And then the way that we make them do things is we arrange them in circuits, right? So we take our gates, we make circuits, and then it's those circuits that do cool things. So let's see if we can find a quantum analogy for that. That's actually one of the models of quantum computation is the circuit model. So some things, just general notations with circuits. If you see something like this, it's a quantum wire. So we're feeding a single qubit quantum state across this. Something like this is I just barred an L. That's great. Is a classical wire. So here we're sending just a classical bit, a 0 or a 1. If you see, again, something like this is a measurement gate. So we take our qubit, which is in superposition potentially of ket 0 and ket 1, and then we collapse it and force it to pick one of those two sides with the probabilities given by the coefficients. And again, if you see it Like this, usually that just means a 0-1 measurement. If you see this with a D, that means like a ket plus, ket minus measurement. Then just a box with like a U in it, or I think we'll see H, X, and Z. This is just a quantum gate. And then the other fun one we'll run into is this is the C0 gate. So yeah, I think that pretty much, for the most part, encompasses most of what we'll see. There's one exception, but I'll get to that when we get there. So, all right. Build a circuit. This is where the fun begins. All right. So let me draw a definitely completely random and not planned out beforehand circuit. I don't know. I think Hadamard gate right there look good. And then let's throw a C naught in there. Why not? Okay. So this here is simple little circuit. This guy is here's doing the brunt of the work. And what we want to do is we want to figure out what is this psi we get out the other end? What state do we end up with? It'll be a 2-qubit state. Actually, it's a 2-qubit state. It's a full state. I should make a capital psi. So now let's work through this. How are we going to analyze this? So we start, our starting state is ket 0 tensored with ket 0. What we do is we take the guy on the first wire, tensor it, the guy on the second wire. Then we run through up to here, and we see we apply a Hadamard gate to this guy and then nothing to this guy. So the full gate here, when you see something like this, an empty wire underneath a gate, what that really means is we have just an implicit identity gate there. Don't do anything to this guy, apply the Hadamard to this guy. So why these pens are too thick. Okay. Let me just there. Okay. So here we apply a Hadamard to the first qubit, which gives us 1/√2 ket 0 plus ket 1. And then we keep the second guy the same, tensored with ket 0. And then distributing out the tensor product here, ket 0 tensor ket 0 is 0 tensor ket 0 plus ket 1 tensored with ket 0. And then in the shorthand notation, this is just ket 0, 0, and this is just ket 1, 0. So this is 1/√2 ket 0, 0 plus ket 1, 0. Then going through to the second guy. So past this guy, here we apply the C0 gate. It gives us 1/√2. If we apply the C0 gate to ket 0, 0, we get ket 0, 0. And then if we apply the C0 gate to ket 1, 0, we get ket 1, 1, as we saw up here. This is ket 0, 0 plus ket 1, 1. And this is the state that we get out the other end of this circuit. Okay, looks pretty simple, unassuming. I think there's no problems at all with this guy. This guy actually has a fun little property. Now, suppose we want to measure. Say we have Say we then take our 2 qubits, because remember, each of these states is an individual qubit. Like each of them is a state of a particle. So we take those 2 particles, Alice has one of them, Bob has one of them. And say Alice makes a measurement. And say she measures a 0. So if you notice in our state here, only this term here has a ket 0 in the front. So what that does is that forces Bob's to be 0 as well. So if Bob measures at any time, exactly the same time, slightly after, 377 years later, he's going to measure ket 0. I guess, actually, maybe after enough time, the wave function would have had enough time to re-wavify. But if he measures pretty much instantaneously after, he's going to get ket 0. Anyone see a problem with this? Okay. So now, what happens if, say Alice and Bob are just sitting in Gentino's cryptography class, they prepare their qubits, and then all of a sudden, Bob has an intergalactic business trip and has to go completely out of the galaxy. And Alice goes to the complete other side of the galaxy. And then randomly at the same time, they're like, oh, I want to measure my qubit. Alice measures, gets a 0. Bob measures it exactly the same time. He's always going to get a 0. How do the qubits know? How does this guy know that he has to be 0? This is if you've ever heard of quantum entanglement, that's what's going on here. This is an entanglement state. There's this one specifically is, you'll see Tino use beta 00. The beta comes from Bell, is the guy that kind of was working with it. Actually, what happened with this state is Einstein and a couple other guys looked at this and said, yeah, no, this is a problem, because how are the qubits communicating? The information can't travel faster than the speed of light. This is quite clearly faster than speed of light travel. So that kind of, Copenhagen interpretation of quantum mechanics can't work because of that. Then this other guy, Bell, used this circuit here and the 4 states that come out of it. This state is what happens if you put in 0, 0. If you put in 0, 1, you get a different one. Same for the other basis states. And used it to show that a hidden variable theory couldn't work, and the Copenhagen interpretation was the only one that was left. So Einstein's like, no, Copenhagen interpretation is wrong. Look at this state. And then Bell was like, actually, this kind of backs up the Copenhagen interpretation. So physicists doing fun stuff. But the other way you might see this denoted is capital phi. Capital phi with a plus. Yeah, we here all pretty much just generally stick to this one. But if you ever see this one, just know it's the same state. And then I think the way that physicists generally interpret at this point the information paradox here is that even from this far away, you know exactly what you're going to measure. You know you're going to measure the same thing, but you don't know from the start what that thing is going to be. You've got a 50-50 probability of it being ket 0 or ket 1. So there's not really anything that you can do with that. You're not really transmitting information per se. It's just that these guys, are the same. It's almost like if Luke and I were to flip coins right now, we know the coins are going to flip the same thing, but I can't really use that in a lot of really useful ways because I don't know what the coin's going to give me. So I can't make like an instantaneous communication protocol because it's just a bunch of random coin flips. Yeah, that's entanglement. I would ask if that makes sense, but it really doesn't. So, but did the circuit trace make sense? Okay. then how much time do we have? Okay, another 20 minutes or so. I could, all right, I won't walk through this, but I will note that there's a second approach to doing the trace. Approach number 2, and that's remember that each of our quantum gates are just matrices. So we take our vector, we're passing it through, this guy's just a matrix, this guy's just a matrix, and then at the other end we get a vector. So we could just view this as a big matrix vector multiplication. So first we start with our ket 0, 0. And then we multiply by this H tensor I matrix, H tensor I. Then we multiply by the C naught matrix, C times H tensor I times ket 0, 0. And this is going to give us the same state out the other end. And then this is really, you're working with 4x4 matrices, but using clever tricks, we can reduce it to a 2x2 case. So, Luke remembers my clever tricks. But yeah, it was just, if you view it as a 2x2 matrix of 2x2 matrices, you can take advantage of the fact that the C naught matrix looks like this guy, and then you can work with the fact that this, if you just throw the I into the Hadamard gate, you have a 2x2 matrix of 2x2 matrices right there just because of how the tensor product works. And then this ket 0, 0 is ket 0 tensor ket 0, which is 1, 0 tensor ket 0, which is ket 0, and then just regular 0. So this is just a 1x2 vector of 1x2 vectors. Yeah, I should note that this 0 is 0, 0. So it's, yeah. It's not just the scalar 0, it's a vector 0. But that's the second approach to analyzing that circuit. Okay, so now we've seen a 2-qubit circuit. But we have these entangled guys now. We can create this entanglement, and then this feels like something that breaks the universe. And we have been handed the keys to break the universe. So what are we going to do? Teleportation. Yeah. So consider the following scenario. Say Alice and Bob have an entangled pair. And generally, we draw a little squiggly line to show these two guys are entangled. I don't know if that's mathematical. I know Tino just does it, and then all of us just kind of follow suit and do it as well. So that should be mathematical notation. Anyway, say they're sitting in this classroom, they're goofing off during their Calc 2 lecture or something, entangling quantum states. And then eventually they have to go far away from each other. So Bob goes over to Toronto, Alice goes to Los Angeles or something. And then Alice finds this really cool quantum state. She's like, I just have to send this to Bob. Is there a way that we can leverage this entanglement to make this qubit, or this state, appear over here? Let me just quickly propose the following circuit. So this top part is going to be Alice's part. So this is Alice's part of the half of the entanglement. This part down here is Bob's half of the entanglement. This C naught, Hadamard, then, yeah. So let's take a look at this here. And normally, this gate here, the C naught and then the Hadamard, if you notice, it looks like the mirror of this one, Hadamard and then C naught. And because of some nice properties of the Hadamard and the C naught gate, namely that they're both Hermitian, which means that they are equal to their conjugate transpose, the way that you undo this circuit specifically is just by flipping it. Now, in general, that's not necessarily going to be true, but in this case, it is true that you just flip it and it removes the entanglement. So if you start with an entangled state, you apply the C naught and then the Hadamard, it removes the entanglement. We're starting with two guys that aren't entangled, and then these two guys are entangled. So this is a really fun, clever little trick. Yeah, so our start state is Alice on the first wire starts with ket psi. And then on the second and third wires, we start with this entangled state, 8, 0, 0. Psi is alpha ket 0 plus beta ket 1. And then this entanglement state we saw was 1 over root 2 ket 0, 0 plus ket 1. Then if we distribute out the tensor product, this is, just pull the 1 over root 2 out to the front, get alpha ket 0, 0, 0 plus alpha ket 0, 1, 1 plus beta ket 1, 0, 0 plus beta ket 1, 1, 1. Okay. And here, this is a 3-qubit state. Don't worry, that's the highest I'll go. I won't, it won't get any scarier than this, trust me. But then what we're going to do is, the first step is going through this C naught gate here. So we do the C naught gate. Our control is first qubit, and then the one that changes depending on that control is the second qubit. So this is 1 over root 2 alpha, and then ket 0, 0 under C naught just stayed the same. So this guy stays the same. Same with 0, 1, yeah. So this guy stays the same. Then here, our 1 is the control. So since this is a 1, this guy's going to flip. The 1, 0 goes to a 1, 1. So this becomes ket 1, 1, 0. And then here, the control is a 1. So it flips this 1 to a 0. We have 1, 0, 1. And then next up is the Hadamard gate. We apply Hadamard. Again, remember there's a, I guess here there's the implied identity gates on this wire as well. But we apply the Hadamard to the first qubit. This gives us 1 over root 2 alpha, and then remember, Hadamard on ket 0 is 1 over root 2 ket 0 plus ket 1, and the Hadamard on ket 1 is equal to 1 over root 2 ket 0 minus ket 1. So here it's going to be alpha cat 0 plus cat 1 over root 2, tensored with cat 0, 0, because we're not changing the second two guys at all. Plus alpha, again, we have cat 0 plus cat 1 over root 2, tensored with cat 0, 0, plus beta, cat 0 minus cat 1 over root 2, because this is the Hadamard on cat 1, tensored with cat 1, 0, plus beta cat 0 minus cat 1 over root 2, tensored with, and can I go further this way? Yes, I can. With cat 0, 1. That's a mouthful. Okay, so now you just want to combine everything together. Let's see, this is equal to pulling the 1 over root 2 out, multiplying it by this 1 over root 2 gives us 1/2. We have alpha cat 0, 0, 0 plus alpha cat 1, 0, 0, then plus alpha, this is cat, oh, this should be a 1, 1. Yeah, that should be a 1, 1. Because this one is coming down from here. Sorry about that. Did I get the other two right? Okay, 1, 0, 1, 0, and then 0, 1, 0. Okay, yeah, so this one, I goofed that one. This should be a cat 1, 1. Yeah, I can't even make the it's 8 a.m. excuse anymore because it's 9 o'clock now. So, okay, but then this is going to be cat 0, 1, 1 plus alpha cat 1, 1, 1. That looks a lot better. Plus beta cat 0, 1, 0 minus beta cat 1, 1, 0 plus beta cat 0, 0, 1 minus beta cat 1, 0. Now, notice that here we have a 0, 0 in the first two qubits with an alpha here, and 0, 0 in the first two qubits with beta here. So let's try grouping those together and see what happens. 1/2 at 0, 0. That in the third qubit, then we have alpha cat 0 plus here beta cat 1. Oh, this guy looks familiar. Alpha cat 0 plus beta cat 1. That's just our original state. So this here is psi. So if we have the 0, 0 bit pattern, we have psi in qubit 3. This is the state in Bob's qubit. So yay, we have potentially successfully teleported our state. But just to make sure that there isn't weird stuff happening, we should combine the other terms together too to see what happens. So let's go next to the 0, 1 case. 0, 1. Then draw. All right. So we got 0, 1 tensor. Let's see what happens here. We have alpha cat 1 plus beta cat 0. Ooh. That's not psi. This is psi, but if we flipped the alpha and beta, or if we flipped a cat 0 to a cat 1 here and then flipped a cat 1 to a cat 0 here. But if you remember, that is exactly what the X gate did. So this is almost like if we, actually it is like if we had our original state and then applied an X gate to it. That flips the 0 to a 1, flips the 1 to a 0. Okay. So it's a good thing we kept going. Weird stuff is happening. This is quantum mechanics. What did we expect, though? Weird stuff always happens in quantum mechanics. So next two are the 1, 0. So we get this to be 1, 0, tensored with alpha ket 0. Okay, we're off to a good start. Minus beta ket 1. Okay, so this here is if we took our state and then ran something that kept ket 0 the same and then negated ket 1. That is the behavior of what our Z gate did. So this is Z times psi. Okay. Now, for the 1, 1 case, let's see. There's no way that this one's weirder than the other guys, right? Again, I want to be, okay, there we go. So plus ket 1 tensored with alpha ket 1. Okay, looks like it might just be the X gate again. Minus, let's see. Yeah, minus beta ket 0. Okay, so this one is weirder than the other guys. So it looks like what we did here is we want to find a way, like, what do we have to do to psi to get it to be this? So that's, alpha ket 0 plus beta ket 1. Well, we have a minus beta. So if we apply the Z gate, that would give us alpha ket 0 minus beta ket 1. And then if we apply the X gate immediately after that, that flips this ket 0 to a ket 1 and flips this ket 1 to a ket 0. So what we've got is, depending on the states of the first 2 qubits, the 2 qubits that Alice has access to, we know what gate we need to apply to get out our original state in Bob's realm. Here, we just need to apply the identity to recover ket psi because we already have it. Here, this is where I should mention another property of the Pauli matrices is if we let actually x squared is the identity, y squared is the identity, and z squared is the identity. So to get rid of this x gate, we just need to multiply it by another x gate. To get rid of this z gate, we just need to multiply it by z gate. And then to get rid of this x gate, then this z gate, we multiply it by x gate. Then we multiply by a z gate. And then here the x squared becomes identity, z squared becomes identity, z squared's identity, x squared's identity. Identity, that's probably the identity. Oh, this is quantum mechanics. No, don't worry. Quantum mechanics doesn't mess with the identity. The identity is the identity. Okay. So essentially, if we know what we have here, what these qubits are, then we know what gates we have to apply to recover psi. Does anyone have any ideas as to how we could know what we have here, though? So right now we've got an equal probability of it being in any of these 4 states. How can I figure out what my first 2 qubits are? Any thoughts? Okay. What if Alice, knowing that Alice knows now, if we look here, whenever we have a 1 in the second qubit, we apply an X gate. Whenever we have a 1 in the first qubit, we apply a Z gate. So Alice knows that. She's like, okay, if I have a 0, 0 pattern, I apply the identity. If I have a 0, 1 pattern, I apply the X. If I have a 1, 0, I apply the Z. And if I have a 1, 1, then I apply a Z and an X. Or I tell Bob to do that. So what Alice is going to do is she's going to measure each of the first 2 qubits. If she measures a 0, 0, then we know that we have this state. If she measures a 0 and a 1, we know we have this state. If she measures a 1 and a 0, we know we have this state. And if she measures the double 1 pattern, we know we have this state. So Alice up here in this circuit is going to measure here and here. And then out of that, we get 2 classical bits. So we said we need to apply the X first, and the X happens if the second qubit is a 1. So if we measure a 1 here, and that's what this little filled in circle here means. If this is a 1, then apply this gate. And let me just, sure. Yeah. Then if this guy is a 1, if the first qubit is a 1, we apply a Z gate. Yeah. So then this comes down. Then out the other end, we get psi, which is the state that Alice originally wanted to send. So it's almost like we have these 2 qubits that are entangled. And we're almost kind of using that entanglement as a weird type of quantum channel to send a state from one side to the other. All right. Now, an interesting question that gets brought up is, what if Alice and Bob go arbitrarily far away? Like Bob's on the other side of the universe. And then Alice is like, oh, I want to send this state, which can probably contain some information. And she just teleports it over to Bob. Do I need to call the intergalactic police? Does this break relativity? Or if it doesn't, does anyone have any idea why it might not? What do we need to have access to in order to know what gate to apply here? We need to know what came out of these measurements, right? If this was a 0 or a 1, and then if this was a 0 or a 1. And notice that this here is a classical channel. So we have to send classical bits via our classical transmission techniques from Alice to Bob for Bob to be able to know what to do to recover the state. So even if our entanglement properties can be really funky over long distances, we still have to have a classical communication channel that follows the, you can't have information traveling faster than light. So this here is what makes it so that we don't have to call the intergalactic police. We aren't breaking the law, but we did find a way to teleport the quantum state, which is nice. Does anyone have any questions about that? We covered a lot today. This Luke could tell you this. Getting to this point probably took us 3 weeks in the quantum computing class. So I guess quickly, one other thing I can do is, let's see. Luke over here went to Qiskit, which is the IBM quantum computing platform. You can design your own circuits. And we threw in this gate here, which, if you notice, this here is just the entanglement gate. We're entangling the second 2 qubits. This is just generating a non-trivial qubit here. This is just a rotation. And then here we're applying the teleportation gate. This is the kind of inverse of the entanglement gate, but applied to the first two guys. Then we take a measurement. This here is sending the measurement down to our classical wire. So this is our classical wire. If this guy's 1, we apply the X gate. If this guy's a 1, we apply the Z gate. And then here, this is just measuring the third qubit. So we don't get to see exactly what the state looks like, but we get to see essentially what happens after a ton of measurements. It goes, simulates it, looks like it just over 1,000 times. And here we get about 75% in state 0, about 25% in state 1. Then if I take this rotation matrix, turn it into the Hadamard gate, Hadamard's an equal probability either one. So if we teleport that and then measure, we expect about a 50-50, and we get about a 50-50. So, and this is a fun little way of playing with quantum gates. You can make your circuits, you can see what they do. I think there's a lot of good information too on the IBM platform that walks you through how certain gates work, a few simple circuits. Also, if you're interested in this type of thing, I would recommend this book, Quantum Computation and Information by Nielsen and Chuang. This is, I think, kind of considered to be the Bible for quantum computing. So, and there's also Introduction to Quantum Cryptography here by Vidic and Wenner that Tino gave me to prepare lectures. So next time we'll look into some actual cryptography. But I don't know, I thought teleportation would be kind of fun. So, and then if there are any questions, I'll be around for a few minutes after. But I'll see you guys on Thursday when we'll talk about the BB84 protocol, which I think is probably a bit easier to understand than a lot of the circuit stuff that we were looking at. Okay.